My name is Erik Goodman, and I'm the director of a research center called the Beacon Center for the Study of Evolution in Action that's headquartered at Michigan State University and with partners at Washington and Idaho and Texas and North Carolina A&T State University. And I'm also a professor in electrical and computer engineering and in mechanical engineering and in computer science and engineering. So yes, I spread myself too thin. Yeah, Beacon is a center for the study of evolution in action, and it's one of about a dozen what are called science and technology centers that are funded by the National Science Foundation, each one for a period of 10 years. And after the 10 years, then they're on their own to find funding to continue. So, and Beacon is 8 years into its funding cycle, so we are now engaged in trying to find ways to keep things going as undisturbed as possible at the end of 10 years. Defining artificial intelligence is not easy. First of all, because we've got to agree on what we mean by intelligence. And being human, we have a very human-centric view of what's intelligent. It's basically what people do. Well, of course, that means that you could define artificial intelligence in terms of how closely a program can match the behavior of a human. And we've done that traditionally through the use of the Turing test, trying to see, can we fool a human into thinking that the program is another human? The difficulty is that programs exhibit only a few behaviors. Intelligence is a form of behavior, and computer programs have very limited repertoires of behavior typically. So as long as we stay within the behavioral repertoire of a given program, then we can get behavior that may look somewhat intelligent. But if somebody were asked, now, is that program intelligent? Oh, then the answer is no, because it can't do this, it doesn't have emotion, it doesn't have all these other things that humans do that contribute to intelligence. So that makes artificial intelligence hard to pin down, but we can see in a given domain when we think a program is behaving intelligently. And particularly if we ask it to follow a certain set of specifications and produce what we hope will be X, and instead it produces Y, and we look at Y and we say, that's not what I asked for, but it works, then that's a surprise. And that's typically a very important element in thinking something is intelligent. It's been creative, as it were, in making a solution that we didn't expect. Yeah, the biggest thing has been observation of evolution in nature. Okay, we have an example that says we got here. That's a pretty strong indication that evolution can be an effective process. Now, it took us a long time to get here. We can't wait that long for an answer from a computer, so artificial evolution has to work a little bit differently. But nonetheless, there are many ideas we can steal from evolution in nature, and I've been trying to do that my whole career, seeing more and more things as we learn about how evolution has worked in nature, and we're learning that at a fabulous rate. About 75% of our Beacon faculty and students and postdocs are evolutionary biologists. And guess what? When computer science people listen to the evolutionary biologists, a lot happens, and vice versa. Many of these ideas have to do with what are the conditions under which interesting things evolve. And we look in nature, and the things that we see is nature, first of all, is massively parallel. There are a whole lot of organisms being tested at any one time. And they're being tested in a very diverse set of environments. So often they're isolated from each other for some period of time, but then they come back together. There's some migration and so forth. And we happen to know that that kind of mechanism enables the evolution of things that simply can't be evolved if you put a single population in isolation and let it evolve. That knowledge motivated me back in the 80s to start creating tools with that in mind. So for example, we did an A-life type evolution where we evolved in an environment that had spatial heterogeneity, deserts and oases, and that had temporal heterogeneity. There were seasons, and that had a limited resource that all the organisms there had to share. And that combination of things allowed very interesting behaviors to evolve. We got organisms to evolve that both competed with each other and collaborated with each other to attain a higher growth rate than either population could attain by itself. And we had no notion that that was going to result, and certainly I don't know that we could have devised a pair of populations that would have done that. I had no idea that it would happen or how to do it, how to make it happen. Back in the 90s, I created a tool called GALLOPS, the genetic algorithm optimized for portability and parallelism, okay? And worked hard on that acronym. One of the things that it eventually enabled was for island subpopulations not only to communicate with each other, which others had also done, but to have different representations so that each one was running its own genetic algorithm with its own fitness function, its own environment, whatever it might want. And when individuals were exchanged or migrated from one population to another, then they had to be translated into a corresponding individual in the new environment. Well, this makes possible evolution of things that were considered to be impractical or impossible to evolve up to that time. For example, we put it to work on an industrial problem for General Motors and evolved a structural part of an automobile that had dramatically better performance while having a much lower weight. This, back in the 90s, required 10 computers running in parallel, and they were all just desktop computers hooked up with an Ethernet and so forth. And that was, for us, big compute back then. But we were able to come up with results that were surprising enough, in fact, that General Motors said to us, start a company. We're going to want this stuff, and we don't want to be licensing it from a university. So you start a company, and we'll be your customer. And in fact, the company called Red Cedar Technology that I was a co-founder of is what evolved from that. It's called a lower compartment rail. It's what hooks up the front bumper of a car to the chassis of the car, and the engine mounts are hung off of that. The front suspension is hung off of that, and so forth. And the problem is that has to crush in a very specific way in a crash, or you injure the occupants much more seriously. Either cut off their legs if it folds too easily, or subject them to a broken neck if it stops too quickly and doesn't absorb enough of the energy in the bumper area. So doing that, the design that we produced, the reaction of the GM engineers is, that's not a rail, that's not what they look like. And then they saw the performance and they said, oh, but it's what they should look like. Well, yes, deep learning, there was no such thing back before we had the kind of computational power to allow massive numbers of GPUs to be thrown at a problem. But now that that's there, it means we can consider networks that have many, many elements. And these networks have to be designed in some way and then fitted in some way. That is, you have to decide the topology of the neurons, and then you have to decide or figure out what the values should be of each connection. And the difficulty is that it's easy to find what values should be if you're given a fixed topology, but reinforcement learning, backprop, gradient following, and so forth, is not a very good way to try and find a topology for a neural network. It takes you immediately to the nearest place that it can find, a local optimum, and that's usually not very good. Whereas evolutionary computation is very good at doing global search in an environment where there are lots and lots of different configurations to look at. So what we do for deep learning is break the neural network into a set of modules. And there's human design in that sense, knowing what the modules ought to be to even look at. In the future, we will be able to do without even doing that. That is, we'll be able to evolve the modules as well. But right now, we typically give an evolutionary computation technique a set of modules, and then it decides how many of them to use and which kinds and how to hook them up to each other. And those decisions are made by the GA. And in each case, deciding how good that neural network is done after subjecting it to something like backprop or some other technique. It doesn't have to be that, but it generally is today. So what that allows us to do is now to find neural networks that can behave better than the ones that humans design. And we're doing that. That's being done and published right now in recent years on a regular basis. And in fact, what we're working on right now is trying to figure out how to look at this as a multi-objective problem, where one objective is to get the optimum performance, say out of a classification system, like a CFAR problem, something like that. And at the same time, trade that off versus the amount of calculations you have to do to make one classification, or the total amount that you have to do in order to generate the system and parameterize the system. So we're finding that evolutionary computation allows us to find very good solutions to those sorts of problems that either beat the human design systems in terms of accuracy for a given amount of neurons, or in terms of the number of neurons for a given accuracy. So the Pareto front has shifted away and advanced from where the human-based solutions have been. The question of greediness of an evolutionary algorithm is one that people have banged their head against the wall for years and years. If you're trying to solve a problem in a small amount of time, you need to be as greedy as you can be. You take advantage of everything you can learn about a local landscape and you use it. And what that means is you'll get to a solution that is a local optimum. And if that's good enough for what you need, then that's fine. If the problem is more challenging and sophisticated, that's going to give you junk. And what you have to do is prevent getting stuck in that local optimum. There are lots of ways of doing that. One of the ways is by systematically using stochasticity, that is, adding random noise to the parameters or to the design variables or to the environment in which you're testing the thing that you're trying to evolve, and that helps keep you away from local optima. Another thing, and generate more robust solutions in practice, things that actually work better. Another thing is to use a more diverse environment, not in terms of stochasticity, but different load conditions and so forth. One of the things that we did in our automotive enterprise was look at solving for some load conditions or some constraints in one population, solving for other things in another population, having them feed things together into another population where it had to satisfy both constraints. We're not telling it how to put those things together. It evolves the capability to put those building blocks together into a solution. But that allows it to do much more divide and conquer. And that allows us to solve much more difficult problems than we can if we just follow the gradient down into some local optimum. I think people are just beginning to apply evolutionary computation to deep learning. Okay, it's a relatively new thing. People are now aware, oh, wait a second, there's something here. So it's going to be pursued very rapidly. But today, most of the people who are doing that are practitioners of deep learning rather than practitioners of evolutionary computation, because most of us don't know enough about the deep learning methodologies to make it easy to do. But that's changing rapidly. And what I think will happen is we're going to get much more sophisticated forms of evolutionary computation. There are tools in evolutionary computation, for example, one called lexicase selection, that are just well fitted for applying in deep learning kinds of contexts where you focus on the trouble spots and try and resolve those. So I think the field is going to go a long way, and I think that at some point not very far away, deep learning will be very tightly associated with evolutionary computation in terms of defining the architectures that are needed, which is now the part that is just done with human expertise. Evolutionary computation, I think, can help to democratize AI by removing the need for the deep learning expert, for example, to specify an architecture for solving a particular problem. Deep learning is not one thing for everybody. If you can afford to throw 100,000 processors at something, GPUs or whatever, yeah, you can solve almost anything with a given kind of architecture. But if you're trying to do something on your desktop, you have maybe 4 GPUs. That's about as much as you can load into it. And you don't have the power to just use a kitchen sink type algorithm. You have to find an algorithm that's well suited to the problem that you're trying to solve. Evolutionary computation can make it a methodical process to find an architecture and then to use that architecture and deploy that architecture. So what that enables is tinkerers. I think it can become a cottage industry then to do smaller scale. I mean, we're not talking about what Google does or what Uber does, or but on a smaller scale to be able to actually develop and deploy AI programs to solve particular kinds of problems.